Your mission, Mr. Witt, should you decide to accept it, is to prepare and upload a video on the topic of integers as exponents, breaking down this confusing area into a concise and easy to comprehend topic. Your students are depending on you. Please do not let us down.
Thanks, Agent Angie. All right, ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is on integers as exponents. Let's check it out. In our first examples, ladies and gentlemen, they're asking us to evaluate. Here you'll see that we have in problem number 1, 4 to the third power, or 4 cubed. You'll want to note that your larger symbol, whether it's a number or a variable, is called your base. So this is my base right here, that number 4. Then the superscript, that raised number here, this is called your exponent. And once again, that could be a number or a variable when you encounter it. The meaning of 4 to the third power, ladies and gentlemen, is 4 times 4 times 4. In other words, the exponent tells you how many times to multiply the base times itself. So since I have 4 to the third power, this means 4 times 4 times 4. In addition to that, ladies and gentlemen, since they're asking us to evaluate these problems, you'll need to find out what that answer is. So you'll need to simplify it after you know what the meaning is. So 4 times 4 times 4, 4 times 4 is 16, 16 times 4 gives us 64 as a result, and this is the answer to problem number 1. All right, here we have it, ladies and gentlemen, 64. In problem number 2, we have negative 4 squared. Here we have a quantity raised to the second power. Whatever's inside of the parentheses is going to be raised to that second power. In other words, we're multiplying negative 4 times itself. So this means negative 4 times negative 4. Then, to simplify that, negative 4 times negative 4, a negative times a negative, that gives you a positive result. So your answer is positive 16 for problem number 2. All right, let's keep it moving. Now, number 3, many people have trouble with a problem like this. Notice that I don't have parentheses around the negative and the 2. In fact, you should know that every time you see an exponent, it only applies to the value, the term, the symbol that's right in front of it. So 2 is being raised to the third power, but not this negative in front. So you could very well say that this is the same thing as negative 1 times 2 to the third power. If that is the same meaning, which it is, then that means I can go ahead and expand this further to say that I have negative 1 times 2 times 2 times 2, so that you'll see that it's actually negative 1 that's being multiplied on 2 raised to the third power. To find out the product of this value, you'll end up multiplying everything that you see here. So negative 1 times 2 is negative 2. Negative 2 times 2 is negative 4. Then finally, negative 4 times 2 gives you negative 8. So your answer here is negative 8. And that's your answer for this problem. Done and done. That's problem number 3. All right, continuing on. Let's look at problem number 4. For problem number 4, we have the quantity of 3/5 raised to the second power, or in other words, 3/5 squared. So this could be rewritten as 3/5 times 3/5. You're multiplying that exact same fraction times itself. So all you have to do here is multiply straight across, since you don't have an opportunity to simplify before you multiply, which is my favorite, by the way. So multiplying straight across, you'll have 9 over 25. And that's it. That's the answer. Okay. So that's what we have thus far for our first problems when we're dealing with integers as exponents. Let's see what this takes us now. In our next examples, they're asking us to simplify. And anytime you have a base raised to the first power, it's the exact same base, ladies and gentlemen. It's the exact same symbol. In other words, 3 to the first power is just 3. That's it. There's nothing else to do to this problem. Anytime you have something raised to the first power, it's just going to be itself. In other words, it's saying just have one of 3. All right, well, I just have 1 3. So that's the answer. That's it. That's all you need. That's all you need. So that's problem number 1. Now, for problem number 2, we have 5 to the 0 power. So I always ask my class when I'm teaching, what's the answer to 5 to the 0 power? And they'll tell me, hey, it's 5, it's 0, it's undefined, but the answer is 1. The answer is 1. And the reason for this is because of the identity property of multiplication. Let me show you why anything raised to the 0 power other than 0 is going to always give you a value of 1. Let's check it out. So what we should already be familiar with thus far is 5 to the first, 5 to the second power, and 5 to the third power. And we went over meanings of these problems, all right? In other words, we know that 5 to the third power means 5 times 5 times 5, all right? Which is 125, by the way. And we know that 5 squared is going to be 5 times 5, right? And of course, 5 to the first power, we just said that anytime you have it to the first power, it's just itself. But because of the identity property of multiplication, we should know that 1 times anything is going to be itself, right? So would you not agree that 1 times 5 times 5 times 5 is also going to give me a result of 125 in that case? And knowing that 5 times 5 is 25, I know that 1 times 5 times 5 is also 25. And I also know that 1 times 5 still gives me a value of 5. So showing the fact that 1 is multiplying on everything does not change my final result. It just only confirms that the identity property of multiplication works, because 1 times anything still gives me the same answer, right? So let's look at the meaning of these exponents again. We could say that 5 to the third power means to multiply 1 times 3 5s. Okay. We could say that 5 to the second power means to multiply 1 times 2 5s. And we could say that 5 to the first power means to multiply 1 times 1 5. Therefore, since the 1 is always present, 5 to the 0 power means to multiply 1 times 0 5s. In other words, you don't multiply that 1 times any 5s. You just leave it as 1. You don't multiply any 5s times that. In fact, they're telling you, hey, you don't need any 5s. That's why you have 5 to the 0 power. There aren't any 5s present, but you always have 1 there, because 1 times anything is itself. It's ever present. All right. So, ladies and gentlemen, if you hadn't caught on already, the answer to problem number 2 is 1. 5 to the 0 power, or anything raised to the 0 power, ladies and gentlemen, is going to be a positive 1. And I also went ahead and gave you a little icing on the cake and showed you why that's the case. The identity property of multiplication. There it is, ladies and gentlemen. All right, continuing on. Problem number 3. Here in this problem, remember I said that anything to the 0 power other than 0 is going to give you a value of 1 when you raise it to the 0 power. And this is why they're giving us a condition in this problem. They're saying that your variable a cannot equal to 0. It can equal to anything else but 0. So you don't have to worry about us getting an undefined situation, because 0 to the 0 power is undefined. Take note of that. So problem number 3, I'm going to show that I have 3 times a to the 0 power, which, since it's not going to equal to 0, is still going to give me a value of 1. Remember, anything to the 0 power other than 0 equals to 1. So this becomes 3 times 1, ladies and gentlemen, and then you'll just find the product. You'll simplify it. So 3 times 1 is still 3, and that's my answer. That's it. 3a to the 0 power equals to 3. And that's it for problem number 3 there. Now, looking at problem number 4, we have a negative base raised to the 0 power. Remember, regardless of whether the sign is positive or negative, anything raised to the 0 power other than 0 is going to always equal to 1. And that's the answer. That's it. So you see any base raised to the 0 power, that answer is going to be 1 every single time, ladies and gentlemen. There you have it. Okay, so that touches on bases raised to the first power, which are always itself, and also bases raised to the 0 power, which will be equal to 1, ladies and gentlemen. All right, so let's check out what it goes on next. Next, we'll be talking about negative exponents, right? And here our directions say simplify with positive exponents. So when asked for exponential notation in your answer, you always want your exponents to be positive. And even further, you're going to still be responsible for simplifying these results when you can. So we'll start out with problem number 1. Notice that I have my base of 3 raised to a negative exponent. Anytime you're given a negative exponent, your first goal is to get rid of those negative exponents. So in order to do that, you can simply shift the base from being in the numerator to the denominator, or from being in the denominator to the numerator. For instance, I can show that 3 to the negative 2 power is currently over 1. Note that you can place any value over 1 and it'll be the same result, right? Well, now I'm showing clearly that 3 is in the numerator. If I were to shift this base of 3 to the denominator, I would end up changing the sign on my exponent. So this becomes 1 over 3 squared. The reason why you have 1 in the numerator, remember, is because 1 is multiplying on everything. So currently in the numerator, this was 1 times 3 to the negative 2 power. So this 1 gets left there in the numerator. So what I actually shifted was this base of 3 down to the denominator, and when you move from either the numerator to the denominator or from the denominator to the numerator, you must change the sign on the exponent and only on the exponent. So we currently have 1 over 3 squared. Well, that's not your answer. Your answer, ladies and gentlemen, is going to be 1/9. All right? So remember, you're responsible for simplifying the result always. Your first step, get rid of the negative exponents. Second step, simplify your result. And there you have it. That's problem number 1. In problem number 2, we have a to the negative 3rd power. All right, so my first step here is to get rid of that negative exponent. So I'll be placing the base of a in the denominator. When I do that, that changes the sign only on the exponent, not on the base of a. It remains positive, but my exponent sign has changed from a negative exponent to a positive exponent. Remember, you're going to always place this under 1 if there are no other terms that are left in the numerator. It's never going to be 0. It'll never be just by itself. When you're moving it from the numerator down to the denominator, you'll always place a 1 in the numerator there because 1 is ever present. Remember, everything's being multiplied by 1, even u. 1 times u is u, just like Mr. Witt times 1 is Mr. Witt. Well, just saying. All right, I'm going to put a box around this because I like boxes around my answers. All right, there you go. That's problem number 2, ladies and gentlemen. For problem number 3, notice that we have a base of 2 in the denominator that's raised to a negative exponent. As I told you before, that you can always change the sign on these exponents by shifting the base either from the numerator to the denominator or from the denominator, the bottom, to the top, which is the numerator. So I'm going to move this base of 2 up to the numerator. So what happens is you'll end up with 2 raised to the 5th power, which is over 1, so you don't really have to write that. So you can just move this base to the numerator. You won't have a denominator worth showing anymore. So 2 to the 5th power just equals to 32. That's right. 2 to the 5th power, 2 times 2 times 2 times 2 times 2. That gives you 32 every time. And this is the answer to problem number 3, ladies and gentlemen. That's it. Just shift that base up to the numerator, and you're done. Let's look at our next problem. In problem number 4, we have 5z to the negative 4th power. As I told you before, your exponent only applies to the symbol that's right before it. So z is raised to the negative 4th power. If you want to know what the exponent is on the 5, well, that's just going to be 1. That's it. Your exponent on that 5 is to the 1st power. How do you know that? Because it wasn't shown, and you don't have to show that something's to the 1st power. So every base is being raised to the 1st power if it's not shown originally, okay? So this 5 is to the positive 1st power, whereas your z is raised to the negative 4th power. That means that in order to get rid of my negative exponents, I only need to shift the base of z, not the base of 5. So that means I'll end up with a response of 5 over z to the 4th power for my answer. Because I didn't have to shift that base of 5 to the denominator, it stays on top. I only had to shift the base of z down below, and that's it, to change the sign on that exponent. So my answer here is 5 over z to the 4th power, and that's my answer. Done and done. All right, next problem. Looking at problem number 5 here. We have c to the negative 3rd power over d to the negative 2 power. Now, in the numerator, I see I have a base with a negative exponent, and also in the denominator, I have a base with a negative exponent. You're not going to find the reciprocal, although it'll appear to be the case. What you're actually doing is, because this base in the numerator has a negative exponent, you'll be shifting it down. And then since you also coincidentally have a negative exponent on the base in the denominator, you'll be moving that up to change the sign on that exponent there. You will not always just be flipping the fraction to get your response. It's only the case here because both bases had a negative exponent that you'll end up with a result that is d squared over c cubed, and this is my answer right here. Done and done. Okay, on to the next problem. All right, here they're asking us to multiply. Anytime you're multiplying like bases, all you have to do is add the exponents, ladies and gentlemen. So the product rule for exponents with integers is when you are multiplying like bases, you will simply add the exponents. In other words, n to the 3rd power times n to the 20th power results in n to the 3 plus 20. Well, 3 plus 20 is just simply 23. So my answer here is just n to the 23rd power, and that's it. So remember, multiplying like bases, just simply add the exponents together and you'll get your answer. Done and done. In problem number 2, we have x to the 4th power times x to the 1st power. Remember, we know that this exponent here is 1. Remember, it's okay to assume that the exponent is 1 if it's not being shown. That is the case. So I'll be adding together 4 plus 1 to give me x to the 5th power as my result for this problem. So anytime I'm multiplying my like bases, because I have a base of x here and I have a base of x here, you just go ahead and add the exponents together. And that's it. Let's look at the next problem, shall we? In problem number 3, I have a to the negative 11th power times a to the negative 3rd power times a to the negative 7th power. Yeah. You're going to add all these exponents together. Notice that all your variables are the same, so that won't change. So I definitely will have a in my result. And combining together, negative 11, negative 3, and negative 7 will give me negative 21 as my exponent. However, you're not going to leave your result with a negative exponent. The only time it's okay to leave a negative exponent in your answer is if they're specifically asking you to leave a negative exponent or you're dealing with scientific notation. All right, so that's not the case here. So we're not going to stop with just a to the negative 21st power. You're going to end up moving that base to the denominator, and it'll be under 1, of course, and you'll have 1 over a to the 21st power, and this is going to be your answer right here for problem number 3. That's it. All right. What do you think? That 21's ugly? I think so too. Can I fix it? I don't know. I'm going to try. Let's see. That's a 2. That's a 1. It's still ugly. Let's move on. All right. So problem number 4. Here we have it. Problem number 4. I have the quantity of m to the 4th power n times the quantity of m squared n to the 7th power. And I want to find out the product of this. I want to multiply these together. So what you're going to end up doing is you're going to end up multiplying your m's together, m as in Mary, and then you'll multiply your n's together, n as in Nancy. So m to the 4th power times m squared, that gives me m to the 6th power. I simply added the 4 plus the 2 together to give me the m to the 6th power. Then multiplying n, which is to the 1st power by the way, times n to the 7th power, you'll end up with n to the 8th power. Recall that this n has an exponent of 1. So I said m to the 4th power, m to the 2nd power, 4 plus 2 gave me 6, n to the 1st power times n to the 7th power, 1 plus 7 gave me 8. And this is the answer to that problem, ladies and gentlemen. That's it for problem number 4 on this page. Let's move on. With our next problem, we have to simplify. Anytime you have a monomial, meaning one term, terms are separated by plus or minus signs. So notice that I don't have a plus or a minus sign within the parentheses. So this is one term inside of the parentheses. Anytime I have a monomial raised to an exponent, you're going to multiply all the exponents by that value on the outside. Okay, so the value on the outside, in other words, this exponent on the outside is 4. So all of the exponents inside of the parentheses will be multiplied by 4, and then you simplify. So let's see what that looks like, all right? Note that this base of 3 has an exponent of 1. So I'll end up with, initially, 3 to the 4th power, because I have 1 times 4. This will be x to the 8th power, multiplying 2 times 4 on those exponents. And this will be y to the 16th power, which is the result of multiplying 4 times 4. Now, you won't leave your base raised to an exponent like this. No. As long as the value is reasonable, okay, like under 100 or around 100, then you're expected to find out what that answer is. So 3 to the 4th power is the result of 3 times 3 times 3 times 3, and that value is 81. So my answer that I'll submit is 81x to the 8th power, y to the 16th power, and I'm going to put a red box around that because it's correct. And I'm done. That's it. That's the result of problem number 1 there. Let's take a look at the next one. Here in problem number 2, I'm given a quantity xy raised to the negative 3rd power, which is all being raised to the 6th power. Remember, if I don't see an exponent, you know it's got to be 1. So this is x to the 1st power times y to the negative 3rd power, all being raised to the 6th power. Remember, multiply your exponents. So I'll end up with the following. I'll have x to the 6th power times y to the negative 18th power. but I will not be leaving my answer with a negative exponent. Instead, since I have a base raised to a negative exponent, I'll be shifting that base to the denominator. So I'll end up with the following. It'll be x to the 6th power over y to the 18th power. All right, and that's my answer there. I'm going to put a box around that. There we go. That's it. X to the 6th power divided by y to the 18th power, and that's the answer, ladies and gentlemen, of problem number 2. All right, here we have the next one. Problem number 3. With problem number 3, I already know that my base, all right, of 2 is going to be to the 1st power because it's not being shown. I have the whole thing, that whole quantity, raised to the negative 2 power. Now, the way I'm going to tackle it is I'm just going to distribute the negative 2. I'm just going to multiply it in. So this negative 2, I'm going to get my arrows popping here and just multiply all those exponents times negative 2. This gives me the following result. I'll have 2 to the negative 2 power and a to the negative 6 power, just like that. Since both of my bases have a negative exponent, they'll be shifted to the denominator. It'll be under 1 because I don't have anything remaining there. So this will be 1 over 2 squared times a to the 6th power. Okay? Then, knowing that I have nothing but positive exponents now, we're not going to leave our answer like that because we know that 2 squared is just 4. 2 squared means 2 times 2. You'll end up with 1 over 4 a to the 6th power, and I'm going to put a box around my answer because I'm done with that problem. That's right. Done, son. That's it. That was problem number 3. Let's move on to the next problem. Here we're asked to divide. Anytime you divide like bases, the quotient rule for exponents is that you're going to subtract the exponents on your like bases when dividing. And you should note that anytime you have a fraction, that operation is division. So 5 to the 8th power divided by 5 to the 6th power gives you the following result. It's the same as having 5 to the 8 minus 6th power, which is 5 squared. All right, well, that answer needs to be simplified, so you'll end up with 25 as a result. And that's it. Done and done. That's problem number 1. Just subtract the exponents and simplify. Then, problem number 2. With problem number 2, I have y to the 9th power, and we should know that in the denominator, y is raised to the 1st power. So you'll end up subtracting the exponents here. So 9 minus 1 gives you 8, so this is just y to the 8th power. And that's it. That's my answer. Done and done. Continuing on. In problem number 3, you'll subtract your exponents, but I will tell you this, ladies and gentlemen. I'm going to show you 2 methods of doing this problem. When I'm working out a problem and I have nothing but positive exponents, I know that my variable will remain wherever the largest exponent is. So since I have m to the 12th power under the m to the 6th power and 12 is larger than 6, I know my variable m will remain in the denominator. It stays there. Then you just simply take the difference of the exponents. And 12 minus 6 is just 6. So I know that my answer here is just going to be 1 over m to the 6th power. And that's it. So once again, my base will remain wherever the largest exponent is. However, if you want to be consistent, then don't fret. You can still subtract the exponents here. So working out this problem another way, you can simply say that you had m to the 6th power over m to the 12th power and you subtracted the exponents. That would give you m to the negative 6th power, right? So 6 minus 12 gives me a negative 6. So you'll end up shifting that base into the denominator to get m to the 6th power in the denominator under 1, which is the same result that we had before. So remember that there are a couple of ways to tackle it, but in this problem I was able to skip 2 steps because I was able to just simply identify the fact that my variable will remain in the denominator. All right, that's problem number 3. Let's check out problem number 4 now. With problem number 4, we have x to the 7th power divided by x to the negative 2 power. One way to tackle this problem is to recognize that you have a negative exponent. Well, I want to get rid of those negative exponents first, so I'm going to bring this variable in the denominator up to change the sign on the exponent. This gives me a result of x to the 7th power times x squared. See, everything's in the numerator now, so I don't have to place it over anything. Now I'm multiplying like bases. When I multiply like bases, I add the exponent. So x to the 7th power times x squared gives me x to the 9th power, and this is the answer to that last problem for division, ladies and gentlemen. Done and done. All right, let's check out our next example. Okay, here they're asking us to simplify, ladies and gentlemen. So in problem number 1, I have a to the 5th power b cubed over a squared b. Remember that the base will remain wherever the largest exponent. So in this problem, my a will remain on top because I'm comparing 5 to 2, and 5 is bigger. And then for my b's, I'm comparing 3 to 1. Remember, if you don't see that exponent, you can assume it's 1. So I'm going to subtract my exponents. This gives me a to the 3rd power, b to the 2nd power, and that's the end of that problem. That's it. Done. Yep, it's over. Problem number 2. In problem number 2, I have x to the 8th power, y to the 4th power, divided by xy to the 3rd power. Well, once again, my numerator's exponents are larger than my denominator's exponents, and they're all positive. So that means I simply subtract the exponents again. Here I'll have 8 minus 1 gives me x to the 7th power. Then I have 4 minus 3, so that's y to the 1st power. And please do not write that 1. It's not necessary. It's redundant. You don't need it. So therefore, I'm just looking at a result that's x to the 7th power y, and done. That's it for problem number 2. Problem number 3, ladies and gentlemen. Let's check it out. Here I have 24a to the negative 7th power b to the 6th power over 40a to the 12th power b to the negative 3rd power. Well, I always love to attack my coefficients first when possible. And so here the 24 and the 80, I know that could be reduced by 8, right? And then I'll also take a look at these exponents, especially the ones with a negative exponent. And I'll be shifting the base of those variables that have a negative exponent. So this is what you'll see initially from me. I'll have 8 going into 24 3 times. I know that 8 goes into 40 5 times. I have 3 b to the 3rd power, b to the 6th power, over 5 a to the 12th power, a to the 7th power. So what happened here, ladies and gentlemen? Not only did I simplify the 24 40ths to give me 3/5, but every base that had a negative exponent, I shifted it. So that meant that a to the negative 7th power, I brought that a down to make it a positive 7. This b to the negative 3rd power, I brought that base of b up so that it became b to the positive 3rd power here. So now that I have this result, I can continue to simplify this problem by combining these like bases in the numerator and the denominator. So you'll end up with 3b to the 9th power, multiplying like bases, add the exponents, and in the denominator I have 5a to the 19th power. And this is the answer. Done and done. 3b to the 9th power over 5a to the 19th power. And that's the answer. Just like that. Okay? Let's look at our next problem here. Problem 4. In problem 4, I have the same scenario where I have bases with negative exponents, and I also have an opportunity to simplify my coefficients, those numbers in front of the variables. So I know that 3 and 18 can both be reduced by 3. So 3 goes into itself once, 3 goes into 18 6 times, and then I'll be shifting those bases that have negative exponents, but only those that have negative exponents. So I'll end up with the following. I'll have c to the 3rd power, d to the 7th power, d to the 4th power, all over 6c squared. So because I had negative exponents on this c, I brought it down to the denominator. Because I had a negative exponent on my c in the denominator, I brought it up to the numerator. I had d to the negative 7th power, so I brought that up, so it became d to the positive 7th power. Yeah, and I just simplified that 3/18 to 1/6. All right. Note that my variable c has its highest exponent in the numerator. That tells me that c remains on top. So I have c here. Because I'm multiplying like bases, d to the 7th power times d to the 4th power gives me d to the 11th power. All of this is going to be over 6. I don't have any c's left in the denominator, remember, because we subtracted to get c to the 1st power in the numerator. And this is my answer. That's it, ladies and gentlemen. I got a box around that because I'm done. All right? And that's it. That's how you manipulate integers as exponents, ladies and gentlemen. And that does it for today's lesson on integers with exponents with Mr. Witt and Fort Bend Tutoring. And a shout out to Angie C., ladies and gentlemen, for her incredible help on the intros and outros. Peace.
Congratulations, Mr. Witt. Your mission was a success. Would you please rate, comment, and subscribe? Also, please visit Mr. Witt's website at tutormemath.net. That's tutormemath.net.